Hi. Now it is section 3.11. In this section, we'll study linearization and differentials, which are approximation techniques. In general, the tangent line to a curve y called f of x at a point A is given in this way when the function f is differentiable at a. That is slope, and a and f of a is the point. So this is the point-slope form of the tangent line. Let's look at the picture. And this is a function, and that is graph of the tangent line. Now, and if we choose x near around a, okay, here now x, then now f of x, that is this value, that is f of x. Now, but the value f of x can be approximated by using here L of x, so that the tangent line can be a good approximation of the function value. As far as they are near each other, close to each other, and that'll be really good approximation here. And officially we define the linearization of the given function. If f is differentiable at point A, then the approximating function and L of x defined as that way, that's the same as this one, is the linearization of f at a. That is definition. And the function value can be approximated by using the linearization. Then in this case it is called linear approximation or tangent line approximation. Of course, A is the center of the approximation, and f of a and L of a have the same value. Now let's solve some examples. Find the linearization L of x of fx given in this way at a equals 0. To find the linearization, we have to find f of a and f prime at a. Right? So here, a is 0 is given. Now f of a, which is now f at 0, that is 2. Quite easily from the definition of f, we can see f0 is 2. And we have to decide also f prime at a. First, f prime is same as now 3x squared and minus 3. So from this one, f prime, okay, a equals 0 now. That is same as minus 3. So we got everything to get the linearization. That is f of 0 is 2, and slope is now minus 3, and x minus 0, right? So that's the linearization. You can simplify yourself. Okay, now again, find the linearization of f given in this way. Okay, now a is minus 8, and f of a, which is f of minus 8, that is the same as now minus 8 of third power. Okay, then that is same as minus 2. Now how about f prime? The derivative of f is now 1/3 will come out, and x to the minus 2 over 3. Okay? So that from this one, f prime at a, that is minus 8, that is same as now 1/3 times minus 8 of minus 2 over 3, which is, this portion is 1 over 4. So 1/3 times 1 over 4, which is 1 over 12. So here we have the linearization, that is f of a, which is minus 2, plus now f prime at a, which is 1 over 12, and x minus a, which is plus 8. Right? That's the final answer. Now, again, one more time, we have to find the linearization of fx, which is 2 tangent x at a is pi. Okay, a is pi. Now, how about f of a? That is same as a is pi, so that 2 times tangent pi. Tangent pi is 0. We can easily see that. Now, tangent is slope, and so that is, if it's 0, then slope is 0. Once pi, then that direction, this is angle pi, and slope is 0. Okay, now how about the derivative? F prime, that's twice of the derivative of tangent is sec squared, so that from this one, f prime at a, which is pi, that is same as now twice of sec squared pi. Second is 1 of cosine. Cosine pi is minus 1. Its square is 1, and also its reciprocal is 1, so that finally f prime at pi is 2. Okay. So here the linearization is the same as f of a, that is 0, and slope is now 2, and x minus a. Okay, that's the final answer. Now, we have to use linearization, linear approximation, to estimate the given number. Okay, 1.002 and to the 50. So once you want to use the linearization and linear approximation, then you have to consider the background of function. So for given term, fx must be here x to the here 50, so that we can choose a is 1. We have to make approximation and centered at 1, and then as a small perturbation, then with 0.002 perturbation, you can get really good approximation. Now, if we go back to the picture, then a is 1, now x is here 1.0002, and now rather than this f of x, we are trying to find L of x to approximate the f of x. Okay? Okay, let's go back to the problem. Then, okay, for that one, we will make L of x, a linear approximation. Okay, now a is 1 and f of 1 equal 1 to the 50, which is 1. How about the slope? F prime is same as 50 times x to the 49. By using power rule, we can get it. And then here, f prime at 1 is same as 50 times 1 to the 49, which is 1. Okay. So here, now the linearization, linear approximation is same as f of 1 is now 1 plus slope is 50, and here now x minus a, x minus 1. That is linearization. So here, Now f of 1 plus 1.002 can be approximated by here now L at 1.0002, which is the same as 1 plus 50. Now that is 1 plus 0002 minus 1. So that is 1 plus 50 times and 0.0002. That portion is 0.01. So that is 1.01. Okay. So the given value is around 1.01. By using linearization, we approximated the end. Okay, let's check what the exact value is. Okay, now here, by using Octave, which is a free version, public version of MathTalent. Okay, let's try to here 1.0002 to the 50. Okay, that is now 1.01. Okay, we cannot see the result, the exact result, because it's the short display. So let's try to make a long display. And again, we write down that, then we can see here the exact value is 1.010049 and so on. So the error is around there. So it's about 10 to the minus 5. Order of 10 to the minus 5 is error. That means that here this approximation is really good approximation. Okay. Now differentials. If we consider the derivative and dy over dx, then it is not a ratio. However, we'll try to deal with this derivative like a ratio. And particularly when the ratio is same as the derivative, then we'll try to consider them as some variable, and eventually dy over dx looks like a ratio. And let's start with a definition here. We start with a differentiable function y equal fx, and here differential dx is an independent variable. Now differential dy is a dependent variable defined as in this way. Dy is the same as f prime x and dx. That means that once dx is given, then dy is the multiple of f prime x and dx. So that now at this moment dy and dx are just quantities, and now from this one we can write over there dy over dx equal same as f prime at x. Now this is the ratio, but we are using this one as a derivative, so that once a ratio is equal to the derivative, then we consider dx, dy some variables, and we say here dy is the differential, dependent differential, and dx is independent differential. Once we define in this way, then what is dy? That's the question. And often the case that the variable dx is chosen to be delta x, the change in x. In this case, the differential dy is a change in the linearization of f, so that is delta L. Now look at this picture here, and now A is the center point, and delta x is a change in x, so that the endpoint over there is a plus dx. So dx is delta x, then dy is the change over there, so that dy is basically the change in the linearization. That means that if we write down that one in this way, okay, L, and here the end point, that is a plus now dx minus L at a. So that is a change in L. So that is a dy. So once you are choosing dx from delta x, same as delta x, then dy is just change in the linearization, so that it is a sort of a continuation of linearization. So we are using the term differentials. However, that is a sort of a related concept from linear approximation. So here, if we go back to the linearization, then we can see in this way. From this one, now we can rewrite this one in this form. That is L of x minus here f of a. That is same as now f prime at a and x minus a. Now that is basically dx, and that portion is now dy. Okay? So once we are choosing dx as the change in x, so it's a delta x, then dy is in change in linearization. That's exactly change in linearization. Okay, so it is quite closely related with linearization. Okay, now we go back to here. Okay, let's try to find the dy, and we try to solve some related problem. Fx is given here, x to the 5 plus 37x. And first part is find the dy. Okay. Now, to find the dy, we have to get f prime x. Okay. So f prime is 5, and x to the 4 plus 37. So that here dy is same as f prime at x, which is here 5x to the 4 plus 37, and here now dx. Right? For any change in x, you can find the change in y. So given change in x, now along with that ratio, you can find the change in y. That's the meaning of here differentials. Okay, we found that. And part B, now we have to find the value of dy when x is 1 and dx is 0.2. Okay, x value and dx is given, then we can find the dy. Okay, here, so the dy is same as x is 1, which means 5 plus 37, as x is 1, so that 1 to the 4 is 1, and dx is now 0.2. So that is here 42 times 0.2. Okay, that's the, so here, okay, if we compute here, that is 8.4, right? Okay. Now, in this example, we'll try to find the differential dy. Just dy in definition is the same as just here dy is the same as f prime at x and dx. So once we can find f prime x, then dy is determined quite easily. Okay, for part A, now y prime equal, now by using chain rule, we can do it in this way. Now, first we consider x squared as a variable, then that is e to the x squared, and derivative of x squared is 2x, so that is same as 8x e to the x squared. So here dy equal f prime, that is 8x and e to the x squared times dy. That's it. Oh, no. That is here dx. Okay. Now, we have to find the derivative, but if you try to do it directly, then it's a little bit complicated. Rather than that, by using laws of logarithm, we can manipulate this logarithm a little bit better way. Because it's a fraction, it is becoming in this way, logarithm of x plus 1 minus logarithm of square root of x minus 1, right? Now again, this is a half power, so that we can rewrite this one in this way. Logarithm x plus 1 minus, that is half of logarithm x minus 1, right? Now, we can get derivative quite easily. Okay. Logarithm of function fx is derivative as f prime over f. So that, that is, derivative is 1. The bottom must be f. Okay. Now, minus half. And now, here, that is here x minus 1, and its derivative is 1. So you can combine in this way, so that, for example, if you make the common bottom, that is 2x plus 1 and x minus 1, then the first portion must be same as 2x minus 1, and the second portion must be x plus 1, right? So that the numerator becomes, now 2x minus x is x, now minus 2 minus 1 is minus 3. Okay, so we found the derivative. So here dy equal same as, now, okay, f prime, which is x minus 3 on the top, on the bottom, that is twice of x squared minus 1. We combine them, and then dx. Okay, that is now dy. Okay, now we'll solve this problem, and we will get dy, the differential, and evaluate it for given data. Okay, so x and dx are acting as data. Okay, first we found here f prime, that is 4x plus 4, right? 4x plus 4. Okay, I rewrite it a little bit better way. And 4x plus 4. Okay. So here, the dy is the same as, now 4x plus 4 and dx. Now x is given minus 2. So here 4 times minus 2 and plus 4. And dx is given 0.1. So that first portion is minus 4 and times 0.1, which is same as minus 0.4. Okay? It's not so much complicated. So once a change in x is given, then we can find the change in y. Now this change in y is measured through the linearization, or just tangent approximation or tangent line. And this is basically the slope of the tangent line, right, at the point -2. Okay. Okay, for this problem, the same way, here y prime equal x to the -1, so the -1 will come out and x to the -2, so that we can say here -1 x squared. So that dy, change in y, is the same as the slope -1 x squared times dx. Okay, once the dx and x are chosen, then we can find the dy, change in y, along with the linear approximation. So by using the data, x is 0.5 and dx is 0.1, we can decide this one -1 0.5 squared and times here 0.1. Now that is half squared, so that 1/4 is reciprocal as now 4, so that -4 times 0.1, so that the answer must be -0.4. Okay? That's the end of the section and end of the chapter. Thank you.